our situation is, I have a C1 map from some larger dimensional space to a smaller dimensional space. So this is R D plus M, which I think of as RD cross RL. And if I have a point X comma Y in here, if I have a point in here, then I think of it as X comma Y, where X is in RD and Y is in RL. And so this point X comma Y is going to phi of X comma Y. And the point P, which I think of, is going to the value C. Okay. So this is given to me, and the key assumption is that so phi prime of P is on. So without loss of generality. So the matrix of this is going to be a wide matrix with M rows and D plus M columns. So we just assume that the last M columns are linearly independent. So they form a basis of R. So without loss of generality, suppose last M columns of the matrix of phi prime of P form a basis of R. So this is non-singular. And notice one thing, just like the inverse function theorem, this means that that matrix has a non-zero determinant. Okay, I should also start recording here.
Recording in progress.
Okay, so I have written the hypothesis for the implicit function theorem, where I have a C1 map from a larger dimensional open set in a larger dimensional space to a smaller dimensional space. And we are assuming that the derivative is surjective at a certain point. Because the map is C1, that means that this M by M submatrix of partial derivatives, since the determinant of that is non-zero at a certain point, the determinant is going to stay non-zero in a neighborhood. So this condition of the derivative being onto is actually going to be true in a neighborhood of the point. As we observed, same thing that we observed in the case of the inverse function theorem. Okay, so this is all of this is suppose. So suppose all of this is true. So suppose all of this is true. Then what do we have? There exists a neighborhood. Okay, so instead of writing the precise statement, let's just write. So then what can we say? That in a neighborhood, I can, or even more. Locally solve phi of X comma Y equal to C for Y in terms of X. So, which is more precisely, there exists a neighborhood W of A such that so neighborhood where? Remember, A is a point in the first slot, which is R to the D. RD. such that, oh, and a map, sorry, such that I can solve. So I need to make a name for the solution. Such that the image of this map is precisely gives me solves for y in terms of x. So what does that mean? First of all, x comma f of x is in U, and y of x comma f of x is. And of course, this should be, this is a neighborhood of A, right? So of course, what we need to have is that f of A itself needs to be. Okay, so, and then furthermore, I can, moreover, okay, so let's see the proof of this. And so we'll choose, remember, so this I have to I have to find this neighborhood W, right? So that we will do later. Let's just first construct this auxiliary map that we saw last time. So I'm going to define this map psi as follows. So first define define this map we called it psi from U to so which is just a souped up version of the old map. So x comma y goes to x comma phi of x. And then we saw that last time that the Jacobian of this map is non-singular at P. So let's just do the calculation. So notice psi prime of P as matrix what? So we did this last time. So this is identity and 0. Because I'm calculating the derivative of only the first slot, x, with respect to all the variables. So derivative with respect to the x slot is just identity. Derivative with respect to the y slot is 0. And then here I will get the derivative of the original function with respect to x and then with respect to. Of course, notice everything is being done schematically here, right? So phi itself is going to have m components, and x is going to have d components, and y is going to have m components. So each one of these is a block matrix. So since I did not write, so here. So what we know is that this is non-singular at P, because the determinant is essentially going to be, so his determinant is equal to determinant of just the lower right part, right? Because of this block triangular nature, and I have the identity matrix. So this is non-singular at P, and in fact in the neighborhood of P, right? In the neighborhood of So by inverse function theorem, psi is invertible in a neighborhood, is invertible with C1 inverse in a neighborhood of V. So let's call that neighborhood something. Of course, we could just shrink the original neighborhood and call and just rename it to be V, but let's not do that. So let us say, so here's now my situation, right? So in a neighborhood, let's say V of V. So here's what I have. This V, and then I have psi of V. The point A comma B, which is my P, what is that going to? We'll just look at the definition of the map. This goes to A comma
C.
A comma C. Excellent. And now I can invert this, right? So let's look at everything. This is now just a matter of writing this. So X comma Y by definition is going to X comma phi of X comma Y. But remember, this map is invertible. So I can write a formula for the inverse. So let's call this general point U comma V. Where does that get mapped? Because if I have a function which is a function with values in, let's say, a function from some set that takes values in a set S cross T, then it really is two functions, right? One is an S valued function and one is a T valued function that you put in each slot. So this is really going to be some function where the second function, let's say I'm going to call f of u comma v, right? So this is the definition of, sorry, not f, because f is the function that I want. So some notation here. So what do I call this? Alpha. So this is definition of which is defined on what set? Defined on which set? Well, it's defined on psi of u. Okay. And in the same way, in the first slot, I can write some other function, right? Beta of u comma v. But actually, I do not need to. What is there in the first slot? Remember this function in the backward direction. This is just the inverse of psi. It's just a dictionary. So in the forward direction, what is psi doing? It is leaving the first slot unchanged. That is, first slot is going to itself. So in the backward direction, it's going to be exactly the same. So what am I going to write in the first slot?
U.
Just u itself. Okay. So let's see what falls out of this. So this tells me that, well, let's just trace. Let's look at the original point. So the original point is a comma b. That goes to a comma c. So which has to come back to a comma b, right? But now I have given this notation. So what this says is that alpha of a comma c is what?
B.
B. So that is just straightforward. But now let's just do this more generally. This says that whenever phi of x comma y is equal to c, let's just go forward and backward. So that means that x comma y is going to go to x comma c, right? I have, so if you want to be sort of painful here, so then here I have x comma y, under the map psi, this is going to go to x comma c, which under psi inverse is going to go to, well, I have the definition. No? So this is going to go to x comma alpha of x comma c. But that has to equal x comma y, right? Because these functions are inverses. So this says that in this case, y has to equal alpha of x comma c. So this is telling me, this is giving me a hint about how to define the function f. Because remember what the function f has to satisfy. It says that if phi of x comma y is c, then I'm supposed to express y in terms of x. Right? And so if to make this even more, so let's turn this once more. So y is, so in other words, if I now plug in this value of y, if I plug in this value of y here, oops, so if I plug in this value of y in here, then what do I get? This simply, and remembering the definition of psi, and phi of x comma, what was y, alpha of xc is equal to, we're just applying dictionary, okay? This is set theory. There is no analysis going on. What is that? Phi of x comma alpha of xc?
C.
C, exactly. So what this is telling me is the following. So we are remember what we wanted to do. We wanted to solve phi of x comma y equal to c for y in terms of x. So whenever phi of x comma y is equal to c, I should be able to tell what y is in terms of x. Now look at this equation over here. What is this telling me? We are forced to define f of x to be y, to be what?
Alpha of x comma c.
And it's all just nice set here, right? Just simple. But there's some kind of problem over here. So I'm defining f of x equals alpha of x comma c, but the question is, what is the domain of this function? Let me first say, but what is the domain of? What should be the domain of this function? Or in other words, the word the is a bit of is not really quite right, but what may be more, but what should we take w to be? Remember, w was supposed to be an open neighborhood, right? So to make this question stark, let me just say, how are we even assured that there is even one point other than a comma b, which is in the inverse image of c? Are we guaranteed? Remember, I'm supposed to say that, oh, this equation, the one that I'm, we started with this equation, phi of x comma y equal to c, and I'm given one solution for this, that is a comma b, right? How do I even know that there is even one other point in the neighborhood? Maybe there is no other solution. That's it, only a comma b. That's the only solution for phi of x comma y equal to c. Do you think that that's possible?
So I think this was these solutions are inverse image of 0 under phi, but phi is C1 and therefore continuous. So
right,
this is an open set.
No, but we see these are inverse images of what? Inverse image of a singleton. By the way, we have not shifted over here, right? So these are inverse images of of C. Notice also there are two functions, right? One is the original function phi, and then there is this new function psi that I have, right? But if you think of the original function phi, then I am really taking inverse image of just a single point C. That's going to be a closed set.
Oh, yes, sir. Yeah, I got
Right.
confused.
Okay. No, so you see, I mean, we should actually discuss all of these things because, I mean, this is interesting. But there will actually be lots of solutions. Okay. So think about where this is coming from. Okay, so you just another way. See, one way of looking at this is that what are we doing? We are trying to describe a level set of this function. Correct? By this function, I mean the function phi. And we want to say, what you will see later on is that we haven't we haven't defined the words yet. But is that this level set is itself going to be a manifold under good conditions. But okay, so a basic question: why should there be even one other point? Okay, so here is the sort of one way of seeing this. Have we really extracted all the juice that we can from the inverse function theorem? The inverse function theorem says that psi is invertible with a C1 inverse in a neighborhood V of P. But it doesn't say only that. And this was a big deal even in the proof. What do we know? What do we know about the image of V? That is also open, you see. So in the image, I have a lot of wiggle room around that point. So let's write this down, which is an open set. But not only is it an open set, it's an open neighborhood of which point? Which is an open neighborhood of A comma C. All right, can you now say something? Show me there are lots and lots of other solutions. So psi of V is open and it contains this point A comma C. Remember, open sets have a lot of wiggle room in all directions. So what should I do? So I'm allowed to shift. So this says that I can take A and disturb it a little bit in the first slot, and I can also take C and disturb it a little bit in the second slot. And all of this is going to be in the image of psi. So we can use this. Should we disturb C?
No.
Not really, because I want this C to be the value of, but I can disturb A, right? Therefore, this contains an open set of the type, let's say open ball W around A. And you see this W is the one that is going to work. So let's check, all right? So this W, so, okay, so, but what is this really saying? Now for any X, by the way, open ball W around A in where? This A is a point in RD, so this is in RD. Now for any X in W, we know that x comma c is in psi of v. Therefore, so now I just look up what okay, so sorry, I'm getting confused myself a little bit with all this set theory, but this should now just take us home free. Okay, so x comma c is in psi of v, i.e. X comma, so I'm just going to take the inverse, so psi inverse of, that means I can apply psi inverse to that, right? So what happens when I apply psi inverse to that? I have the formula, no? That is x comma alpha of x comma c is in v. So what we said is that for every x in w, I have this function alpha of x comma c defined. So you should, if you're not seeing the point, then you should sort of sit down by yourself and see what just happened. It's a very small point, but we did use the fact that the image is open to ensure that I can hold C to be fixed in the second slot, but I can move X in all possible directions to get an entire neighborhood around A. I use that. I use the openness over there. So we define F from W M by taking X to be X to what? Alpha of X comma
C.
Yeah, so I guess some people are saying 0 because you have probably read it from some other source or Professor Pramad's notes, and that is okay, because what you can often do is that what the value of A, B, and C is doesn't really matter, because I can always shift to make those 0, right? But I did not want to do that, because if it is all zeros, then at least I get confused about which 0 is sitting there. So I did not shift. And we are done. And we have the desired function. Okay, so but let us see carefully what we mean by desire. So the reason why this is desired is because of that, right? Remember what I wanted? I wanted phi of x comma f of x to be c, but I have exactly, but this definition of f really ensures that. Okay. This is true for all x in an open set. So I have done that also. What else is left? Let's look at the conclusion. So there is a neighborhood W. So look at the part after I. There is a neighborhood and a unique map. Have I shown uniqueness? Okay, so maybe this is something to think about later. But I have certainly constructed a map F such that x comma f of x is in U. Well, why is that? Because f of x was defined to be alpha of something or the other, right? So remember that the map, everything is happening on one side in U and on the other side in psi of U. In fact, I restricted further to V. And then this last one, phi of x comma f of x is C, that was I mean, we did ensure that. How about f of a being b? Is that also clear? But notice, what is f of a defined to be? F of a is alpha of a comma c. It is b. So the next point is uniqueness of. Oh, okay. So one more thing. How about this? How about this function f being c1? I think that's also and a unique. I should really have said that c1. Is it easy to see that f is a c1 map? Okay, so let us look at how f came about. F was alpha of x of something, right? So what was alpha? Alpha was a component of psi inverse. Do I know anything about psi inverse?
It is C1.
It is C1 because the inverse function theorem guaranteed to me that when the map psi is C1, its inverse is also C1, right? So psi inverse is C1, and that means all of its components are going to be C1, right? If you want, that is because if I take any component of that function, then the partial derivatives of those components are going to be some entries in the big Jacobian, right? But the big Jacobian itself is all entries are going to be continuous. So some of the entries will also be continuous. And therefore, in turn, going backwards in that characterization of C1 functions, now that the matrix of partial derivatives of this component function is continuous, so therefore the component is continuous. And I have to do that once again because you see this alpha of xc. No, okay, I already did it because c is fixed. But so maybe just the thing to say is that this characterization of C1 functions that we had, that a function is C1 if and only if all of its partial derivatives are continuous. After that, we just use it left and right without any comma. Okay, so the C1 is okay. How about uniqueness of f? And you see, the uniqueness of f is actually not in general true. Okay, so in fact, uniqueness of f is not true in general or arbitrary. And example of this is not really difficult to see. So let's look at this case. Okay, so here remember phi of x comma y is x square plus y square, which is a map from R2 to R. So here D and M are both 1. And I take C to be. So the level set over here is the circle. Let me try to do a slightly better job here. Not great, but will serve the purpose. Okay, and now let us say this is the point that I'm taking to be A comma B. So let's see what is required to be done. I want to be able to solve for the y coordinate in terms of the x coordinate. Okay, near the point A. So this is the point A. So what do I take W to be? I'm supposed to take W to be some open set containing A, right? So let us say I take it to be this set, A minus epsilon to A plus epsilon, and let's call this W. Okay. So here, what is f of? So in W, f of x is equal to what? Come on. So I'm supposed to be able to solve in a neighborhood over here. I'm supposed to be able to solve locally for y in terms of x, ensuring that f of a is b. So there is only one way of doing that, right? So what is the formula?
Root of 1 minus x squared.
Square root of 1 minus x. So this seems fine, no? I mean, I got this neighborhood, and the answer really was unique. Now I could not do plus or minus because that would just break the function, right? Sometimes if I wanted to take the positive square root, and sometimes if I wanted to take the negative square root, then in this neighborhood, it would break the function. Okay, so this seems fine. And notice that in the statement of the theorem, I'm saying there exists a neighborhood such that there is a unique C1 map. Not that for every neighborhood for which I can do this, the map is unique. In fact, can you tell me another neighborhood where the map is not unique? Just do something dumb. This is W1, and I just do some absurd thing. So W is the union of W1 and W2. And now you see what is going to happen. Is forced. But for X in W2, do you see what's happening? I mean, this is a very silly point, but do you see what is happening? That in W2, in order to ensure that I am getting Y in terms of X, I can really choose 1 minus X square, or of course, I have to choose positive sign throughout, or I have to choose negative sign throughout on W2, because otherwise the function will be discontinuous over there. But either one will work, right? So, so I have a choice for F on W2. So what should I insist for W in order to ensure that F is unique? Yeah, so we did not really use this concept in class very much, but there was one homework problem, I think optional homework problem early on. So if I insist that the set W be taken to be connected, then this will work. So if W is connected, F will be unique. So let me just sketch this, and if you are, and I think, and try to work this out on your own. So, for example, take. So, if I recall right, remember I think, so I took W to be an open ball, and a ball is connected. If you recall definition of connected set from the homework, a connected set is one such that if I regard it as a topological space, then there is no subset of it which is both open and closed, other than the whole set and the empty set. So the way to show that something is connected is to show that such a thing is not possible. But here, more to the point, is that if you are assuming that W is connected, then to show that F is unique, there is a sort of standard way of doing that. For example, take W to be a ball, and it is a fact that balls. Then F is supreme. And the proof of this is the following. Suppose G is another solution to phi xy is equal to c. Phi of x gx is equal to c for x in w. Then you do the following. This is a standard kind of thing. Consider the set x in w such that f of x equals g of x. Do you know one element of this set?
A.
A. So this set is non-empty. So now what I do is I try to show that this set is both closed and open. And because it is non-empty and W is supposed to be connected, it will have to be all of W. It's a standard way of doing this. So this contains A. Show that another C1 solution, okay, is in fact continuous will work. Show that this set is both closed and open. Is at least one of these easy? Immediate?
Closed is, I think, because this we can write this is a zero set of some function, some
Right,
continuous
exactly.
function.
Exactly. So, so this is a general sort of thing. This comes from you know, you can do this even in point set topology. If I have two continuous functions from one space to another, then the set of points where those functions match each other is closed, provided you have a Hausdorff spaces are Hausdorff, and of course we are working with matrix spaces. So yeah, if you want, so this is like much simpler. Just consider the function f minus g, right? Based on what you were saying. So these are functions into Euclidean spaces. So f and g are continuous, so I can consider the function f minus g. And this is just the inverse image of the singleton 0, the given set. And singleton 0 is closed, f minus g is continuous, so the inverse image will be closed. So this set is closed is easy. So let's call this S. Easy. S is equal to inverse image of f minus g inverse of 0. Now for openness, you have to do something a little bit more. Basically, if you want to show that if a certain point is in this set, then that is, if two functions match at a certain point, then they will also match in a neighborhood. Where is this going to come from? You see, this is essentially going to come from inverse function theorem, because what we are, see, we took this helper function, right? So what is going to happen is that this inverse function, this function is going to be invertible. So the way to come back is going to be unique. Notice that if I mean, there is a little bit of work to do. But notice that this function psi, I mean, if I was given u and v, then alpha was uniquely decided. If I was given if I'm given x, if I'm given u comma v, then there is a unique way to come back to that. So you see, there is really no choice about what I can put in the second slot. So see this. All right. So this is as much as I want to say about the implicit function theorem. One more thing. So we also said, oh, okay. So this also I will calculate the derivative of f. So how do I calculate the derivative of f? Is it easy? Come on. So f was defined after all in terms of which function?
Alpha.
Alpha. Okay. But where did alpha come from? Alpha was a component of
Psi inverse.
psi inverse. So f is really completely determined by psi inverse. So the derivative of psi inverse is, can I calculate that?
From the implicit function theory.
Yeah, see, psi inverse, psi composed with psi inverse is identity that is given to me by the inverse function theorem. And not only that, psi inverse is C1. So I can use the chain rule to calculate the derivative of psi inverse. We saw that, right, in the inverse function theorem. So just apply it. F using okay, so this I will leave for you to do. I do want to do some examples, some more examples using the implicit function theorem. So as long as people are willing, I would at least like to have a class on Monday where I will do some examples. And of course, as I said, I'm happy to take all 3 classes next week if people just want to discuss, ask questions, or if you just want me to work out some examples. But give me some indication, okay? If you want this, then what you would like me to do on Wednesday and Friday. On Monday, we will do a bunch of examples. But today, in the remaining time, whatever, another half an hour, something like that. Yeah. Less. Let's try to do complex derivatives. So, and again, we will not do much other than not even really scratching the surface. We will just maybe smell the subject. But it is absolutely fascinating. And there are things over there that are just amazingly different from what happens for real functions. So let us see complex differentiation. And really the only thing effectively that we are going to prove is the Cauchy-Riemann conditions. So some things to see. So one is that suppose I have U is an open set in C, which I regard as now this equality sign is tremendously fraught. Equal as what? I mean, as sets, yes. As topological spaces, yes. But as vector spaces over R also maybe. But there is one thing that complex numbers are, which the real plane is not, if I just think of it as R2. And what is that?
Algebraically closed.
Right. So, okay. So I can still say a quibble. You see, in R2, I can define a multiplication, right? A very dumb multiplication I can define on R2. Namely, A1 comma B1 times A2 comma B2. I can simply define it to be A1 A2 comma B1 B2. There's absolutely nothing wrong with this multiplication. However, this is very different from the complex multiplication. That complex numbers form a field. The multiplication that I defined doesn't give me a field. No? Just look at it. 1 comma 0 does not have an inverse. In fact, 1 comma 0 times 0 comma 1 will be 0, 0 comma 0. Uh, so what I told you, it is in sort of math parlance, it is a ring, but it's a very dumb ring structure. Whereas complex numbers are a field, and this makes a world of difference. However, as far as topology is concerned, it's the same topology. I consider C with the topology of R. And now suppose I have a function. So consider F real differentiable. Differentiable. F prime A is defined. No, let's so the derivative of F as an operator as a R linear operator from R2 to R2 is defined. Okay. So nothing new is happening over here, right? It's just as before. However, now because complex numbers are a field, if I recall the definition of the real derivative, the exact of R of a function from R1 to R1, the exact same definition can be made over here as a separate definition, and it makes sense. So definition, which is a completely different definition. So it's called complex differentiable at, let's say, some z0 in U, if limit as h approaches 0 of f of z0 plus h minus f of z0 divided by h exists. And then this value of this limit, then this limit is what we call f prime of z0. Notice that two different notations, just to keep our heads straight. df is the operator, is the usual derivative that we have been talking about in this course, and f prime of z0 is what I'm going to call the complex derivative. So there is a lot to understand over here. One is that here h is a complex number, and then this in the field C. I can divide one complex number by another, right? As long as the complex number is that I'm dividing by is non-zero. So this is what I'm going to do. And h is a complex number. What does it mean that h approaches 0? Means
Its magnitude. Yeah.
but again, notice that it can come to 0 in all directions. Okay. So this is sort of, now the problem is nicely set up, which is I have two completely different notions, a priori at least, completely different notions of differentiability when the function that I have is defined from an open set in complex numbers to complex numbers. How are they related? Okay, so there is a very nice relationship, which we will see. You can also ask another question, by the way, which is that, okay, why do we do this only for complex numbers? For real numbers, we really just had any RM and any RN, and then I did this, right? Can we do this for in the multiple complex variable case? Do you see what I'm saying? So we sort of marry the two things. One is I take the instead of RM and RN, I think of those as CM and CN and apply and use the old definition, correct? So I can do that also, but we will stay away from that because that's like doing several complex variables. So here what we are doing is only comparing two things. A complex valued function on an open set in C, and if I take its derivative by imitating your first semester definition of derivative, what that gives, and how do I compare it with the notion of derivative when I regard the same function as something from an open set in R2 to R2. Okay. And so this is one thing. So one, say F is holomorphic on U if F prime Z naught exists, all Z naught. Now, sometimes you may have seen that this is called holomorphic and people say analytic. And in the complex case, they are the same, but the words themselves by definition have different meaning. So okay, let me sort of tell you one punchline right away. And we say the map then the map F prime, which is from U to C, which takes any Z to F prime of Z, is derivative is the derivative of F. So the derivative as a map. Okay. So now for real, in our case, what we saw is that if F is differentiable, is F prime necessarily differentiable? I'm just talking about first semester calculus.
No.
No, certainly not. It need not even be continuous, right? However, this is one of the sort of first amazing things that happens is that if F is holomorphic, then so is F prime automatically in the complex case. So amazing fact. Implies that so is F prime. So you will learn this in complex analysis. So today what we want to do is Cauchy-Riemann conditions. And the idea is so it looks like we are going to run out of time. So let me just say what we are going to do. If a function is complex differentiable, then its derivative is just a complex number, right? And I'm supposed to get the same complex number no matter how I take h to 0. So I can take h to 0 along any line, or in fact along any curve, doesn't matter. I'm always supposed to get the same complex number as the limit of that ratio. So Cauchy-Riemann conditions are what fall out if I take the limit along the two principal along the real and the imaginary direction. So let's carry this. So suppose f prime of z naught exists. That is, f is complex differentiable, where z naught is equal to some a plus ib in open U inside C. Now, here's what we will do. Now, f is a function from U to C, right? That means the point, any point Z is going to go to some other complex number, right? So some complex number, but this complex number is going to be written in the form U plus IV. It's real and imaginary part. So here, U is going to be a function from U to R, and V is a function also from the set capital U to R. It's just real and imaginary parts. So let's write down calculation. F prime of Z naught is limit as h approaches 0 of f of. Now I'm going to say z naught plus h, right? But I'm going to take a specific h. So first take h in real numbers. Okay. So that means that this h is going to be added only to what?
The real part.
Only to the real part, right? So this is going to be a plus h. Okay, so let me, so so let me just change this. H is equal to t, which is in R, and then later on we will take I times t, right? So again, t is in, so a plus t plus ib minus f of a plus ib divided by t. And now let's write this down in terms of, so limit as t approaches 0. So limit as t approaches 0 of. So what is the real part of this? This is real part of a plus t. And let us think of this as a subset of R2, right? Because I want to connect this with partial derivatives of these component functions. So that's what I have. And then the second will be, so not U. So plus U of a comma b divided by t plus limit as t approaches 0. And I can take the I out from here. Just separating out the real and imaginary part. So limit as, so what do I get over here? Exactly the same way. V of a plus t comma b minus V of a comma b divided by t. So what does that give me? I recognize the first one as precisely what? I have a function small u from an open set in R2 to R. And what am I doing? That first calculation, there are no complex numbers left here anymore. It's just a directional derivative, no? In what direction?
The direction of the first.
Right, which is the x. So I'm going to call this as del u by del x at a comma b, so at z naught, plus I times del v by del x at z naught. Okay, so hopefully this is okay, because then the second one we can just take. Now remember, this is f prime of z0. f prime of z naught. So now I can take h equals I times t, where t is again in R. So then what do I get? F prime of z naught is limit as I times t approaches 0, but that's really the same thing as t approaching 0 of what changes now? So what changes? F of a plus, now t is not here, but f of a plus ib, and now it gets added over here, minus f of a plus ib, that stays the same, divided by, divided by what?
IT.
Yeah, not t, okay? Because remember the thing that so the h is the h that I added on the numerator, that's the same thing that I have to put in the denominator, I times t. Okay, now I play the same game as before. So this is limit as t approaches 0 plus I times limit as t approaches 0 of what? So let's write down, this is u of a, and now writing it as something in R2, it is no longer a plus t comma b, but a comma b plus t minus u of ab divided by it. And in the second one, what do I get? The same, exact same thing for v of a b plus t minus v of a comma b divided by it. Okay, very good. So what happens? So let's just take 1 over I to be common. And what do I get now? The first one is del u by del y, correct? Because see, I'm changing b to b plus c. So this is a derivative in the second direction. And again, this is at z naught. And sorry. And then what do I get? Plus I times del v by del y at z naught. So, okay, all nice and good, but this 1 over I makes things interesting, right? So what does that do? So let's write this as a real plus an imaginary part. So the 1 over I is minus I. So what this gives me is that, what does this give?
Like the partial of v with respect to y minus the partial derivative of u, I times partial derivative of
Correct,
u.
exactly. So this 1 over I, or if you want 1 over I and I cancel, and the real part is this z naught, and then I get minus I times now. So this is 1 and this is 2 by 1 and 2, or really let's say equating 1 and 2. What do I get? I get something very nice. F is differentiable. F is not we don't say holomorphic at holomorphic. Often we use that for in an open set. So, but let's say F is complex differentiable at z naught implies what? Real parts have to be equal. That is del u by of the derivative del u by del x at z naught must equal so the partial of partial of real component with respect to x must equal the partial of the imaginary part with respect to y. Because notice those are both real parts of the derivative as a number, okay? The derivative as a complex number. And what? Let's look at the imaginary parts to see. The first one has imaginary part del v by del x. And that has to equal not del u by del y at z naught, but with a minus sign. Okay. So In fact, more is true. So you see now an obvious question arises over here. So this was all okay, which is to say that if f is complex differentiable, then I have partial derivatives, because these limits have to exist by the way, right? Notice that since the left hand, since f prime is defined, the limits, regardless of which direction I come in, along which direction I approach zero, the limits have to exist. So I have shown that the partial derivatives exist and they must satisfy these conditions. But I can ask a bigger question, a seemingly bigger question. Is it real differentiable, in fact? And the answer is yes, it is going to be real differentiable. And if I write down the Jacobian, then in fact I can tell exactly what the Jacobian is in terms of this. So let me just say this. In fact, more is true. So claim under the above conditions for open U in C, if f from U to C is complex at Z naught in U, then f is also real differentiable as a function from U to U, and it's okay. So Jacobian is, and we will get exactly what. So f is equal to U comma V. U and V real valued functions. Jacobian of f at Z naught. So we can just write this, no? So you see, this is going to be what? Ux, the del u by del x, then del v by del x. That is going to be the first column, right? So del u by del x. So all of this is at Z naught. Okay, so let me just say, so what is the Jacobian? Del u by del x, del v by del x, and del u by del y, del v by del, correct? All of this at Z naught. But in fact, we know exactly what this is, right? We can use I can write everything in terms of partials of u, or everything in terms of partials of v. So let's do that. So this is del u by del x and del u by del y. But now what is del v by del x? That is minus of del u by del y. And likewise for the other one. So this is going to be minus of del u by del y. And then this is del u by del x. And similarly, I can write everything in terms of v. So the lower row will stay the same, del v by del x, del v by del y. And what do I get for the top? Del v by what?
Del v by del y minus del v by del x.
Minus del v by del x. Look at the determinant of this. What kind of determinant does it have?
It's non-negative.
Right. So you see, so this is something interesting, right? So anyway, but we are, I think, way out of time. So we should stop. So try to prove this claim. So exercise. And on Monday, we will do examples, but I will also say a little bit more about these things. You know, there are lots of amazing things that happen. So for, for real numbers, if a function is differentiable, its derivative need not be differentiable. But for complex differentiability, we saw that that is not the case. But there are also amazing things about holomorphic functions and their representation by a power series. So for real numbers also, I have the Taylor series, right? And you saw when does, for some functions that, if I take any point, let's say a function has all of its derivatives, a function from R1 to R1, and let's say it has all of its derivatives. Does that mean that the Taylor series at every point converges to that function in a neighborhood of that point?
Not necessarily.
Not necessarily, right? But for functions where this does happen, I give them a name, right? I call them real analytic functions. But this is not always the case. Whereas for complex numbers, if I have a holomorphic function, then just the fact that it has it's complex differentiable in an open set makes all of these amazing things true. So we'll talk a little bit about it. But anyway, I mean, you're going to see all of this in complex analysis. Mainly, so on Monday, I would like to do a bunch of examples. So if you want me to do some examples, please send me an email. Or if you want me to discuss anything specific, then send me an email. On Monday, I would like to have a kind of practice class where we do some examples. And for the rest of the week, it depends on you. So today, with that, let's stop.
Recording stopped.
Yeah, so is there anything else to discuss? Anything anybody would like to say? Yeah, so by the way, in this claim, the Jacobian part is already done, right? So the only thing to show is differentiability. So you have to show that this matrix really does work as the derivative in the sense in which we defined differentiability. But this is really not very much. It's just a little bit of work. All right, so if there is nothing else, then we will stop. So don't forget that your homework, I hope that you all are hard at work on the homework. It's not really a whole lot of work. I have given limited amount of work, but please do the homework and submit it on Sunday. And then on Sunday evening, we have a quiz. Don't forget that. And for each quiz, the portion is exactly what is covered on that homework. So in the homework, I have said, right, that I think on each homework, I have given you 3 theorems. That these are the theorems to know, and you should also have an idea about the proof. Certainly you must know the precise statement, that what is the hypothesis, why are the different hypotheses required, examples, counterexamples. Proof itself, I'm not going to be asking proofs in the quizzes. The final exam will have reasoning based, proof based questions. Quizzes will be mainly examples, and then sort of why different conditions are required, what can go wrong, what goes right, and etc. Okay, so any comment or question, anything?
Sir, about the implicit function theorem.
Yes.
Like I kind of sort of get what it is saying and sort of thing, but like the bigger picture of why this is something that we really want to look at, that's I'm still not able to fully understand that. I looked at the Stack Exchange thread that you shared with us also.
Right. Yes.
I couldn't fully appreciate that answer, and so I'm a little confused. And in addition to this, one thing in particular I wanted to ask is, are we still trying to make statements on, or rather like formalize the idea that locally a function looks like its derivative through the implicit function theorem as well?
Yes. So I think those questions are related. By the way, I sympathize. I should say, I confess that my feeling about the implicit function theorem is still the same. Is similar to what you said.
Okay.
I think the way, one place where you start to appreciate this is when you internalize the definition of what a manifold is. So let me see if I can say something meaningful over here. Feel free to completely ignore what I said, because it's like, in some sense, it's like, I am blind myself. So for me to try to lead you is, okay. I think this is useful. If we just draw the real line, does the real line as a geometric object exist without knowing real numbers?
I guess, yeah.
Right. I mean, okay. And also we are now doing heuristics. Okay. We are talking a bit of philosophy here. And if you ask this question, for example, to, the ancient Greeks, they would just look at you, right? A line is a perfectly beautiful thing. And what are real numbers? Until we sort of all became Cartesians and said, you can just put coordinates, people were able to do geometry perfectly well. So this coordinatizing things is a beautiful thing, but there is something that is intrinsic geometry. Okay, so if we agree that then that means that this is really just one way of, and you saw this in linear algebra, that yes, vector space is Rn and it is a tuple of numbers, but it really is a shackle to always have to think like this, right? You want to say that no, a vector is just an element of a vector space, and a vector space is something which I can handle in certain ways. And yes, whenever I want to choose a basis, I'll choose a basis and put coordinates, but I really do not want to be tied to putting coordinates. I want to be able to think without coordinates. And when you see that, okay, there is a certain operator, even if this operator is from a concrete Rn to Rn, if you want to diagonalize a matrix or something like that, you really do want to be able to change basis, right? So you have seen this already in a linear situation. Okay, so now with this, let's come to geometry. So linearity is okay, but the world is not linear. I mean, we do calculus in order to locally linearize it, but the world is curved. So this means I want to do the same type of thing for objects that are defined for geometric objects, not linear objects, geometric objects. Okay. So what is a geometric object? So manifold is something that is, you can visualize it if you wish as some kind of figure, some kind of shape. This shape even doesn't have to sit somewhere. But a definition of a manifold is that something that locally looks like Rn. So we want a topological space, and the formal slogan is that it should be second countable and it should be Hausdorff. But the idea is that you want to is that a nice kind of space is where locally it looks like Rn. So what does that mean? You picture a circle. Around any point, I can, a circle not as x square plus y square equal to 1 or something like that. Okay, that will come later. But just a shape. And if I, around any point, I can put a small neighborhood, a small segment, open segment that looks like R. I mean, if you want, you can take like the interval from minus epsilon to epsilon, but that really is real line, no? In the sense that I can put a homeomorphism between that and real line. That is a bijection which is continuous both ways. If you want to do calculus, then we say that I can put a bijection which is not just continuous both ways, but it is a C1 function both ways, or C2 or C infinity, depending on what flavor of functions you allow. This is just like school, no? I mean, in school, so and even more sort of heuristic and philosophical things. In that, when are two different things considered the same? This is not even a mathematical question. This is the kind of question that we grapple every time. You have two different 10 rupee notes. I mean, they're different as objects, but in some sense they are the same, right? They're not identical objects, but somehow, as far as some property is concerned, they are the same. So when do we consider two objects as isomorphic? And in school you said, these two triangles are congruent. But then you said, okay, but then I have a different notion of sameness, that is similarity. So when we say two vector spaces are isomorphic, that means that there is a linear isomorphism. So two topological spaces are the same if there is a continuous bijection both ways between them. So depending on what notion of sameness you want, you could say that two geometric things are same if there is a bijection between both of them, that is a C1 function or C2 function or C infinity function. Or if there is some kind of complex structure, then it's biholomorphic. Right? So the details are not important here. The idea is important. So let's put these two things together. So what is a manifold? That means that it's a space, which is a topological space, which locally looks like Rn. What does that mean? That there should be a homeomorphism, a local homeomorphism, that around every point there should be an open set, which is homeomorphic to Rn. That means I'm supposed to give an explicit homeomorphism to Rn. But you see, so now okay, so we say that around this point, then I have this open set, endpoints not included, with which there is this homeomorphism to Rn, which is just projection. So that one. But now there could be this. That is also, and that is this. Now notice that this circle, I'm thinking of it intrinsically. I'm not putting any kind of, I'm not thinking of this as subset of R2 or anything like that. It's just a circle as a disembodied object, if you will. So if I have these two identifying functions for parts of them, then this is like saying that I'm putting coordinates on those parts. So every red point I will identify by means of a number from whatever, -1 to 1. And every blue point also I will identify by means of a number from -1 to 1. So this is like giving two bases for a vector space, but it's a different situation because I do not have an entire vector space on which I am putting two coordinates and trying to relate them. There are two different parts of this geometric object on which I have put coordinates. I put a single coordinate, by the way. I'm describing every point on this red part by means of a single real number. And I'm describing every point on this blue part also by means of a single real number. So what I can say is that I would like these two different ways of identification to be nicely related. And now this is okay, because you see, I have this function, let's say alpha, and I have this function beta. If I take inverse image of beta and follow it with alpha, then I have a function from part of a real line to a part of a real line. And now I can consider whether this function, I can do analysis with this function. Is this function differentiable? So a manifold, a way of defining a manifold is that something that has patches, that is patched up by these many different open sets, each one of which has a dictionary that identifies it with Rn, or an open set of Rn. And all of these different patches, if I go from one patch to another, by means of starting with something in Rm, then going to this abstract object and going to another Rm, then I have all of these functions. They're called transition functions. They should all be smooth functions, or they should all be continuous functions if I want to study this top manifold only topologically. Or I say they're all C1 functions if I want to study them as objects on which I do calculus. Okay, so the sum of everything that I'm saying, in short, is that a manifold is where a manifold is something that is obtained by patching many different copies of Rm in some fashion, in a compatible way. Okay, so you see, when I define, now imagine that this circle itself is part of R2. In that case, the functions that I have, those are some kind of ways of putting coordinates, right?
Yes, sir. Yeah.
So notice that every red point now has two coordinates as what it is, because I'm regarding it as a set in R2. However, I'm describing it by a single number.
Yes, sir.
Right now, so by the way, here I'm floundering a little bit, because this is one way of thinking of the implicit function theorem, but there are other ways. So what I can say is that if I am taking, so what did I do when I did projection? I just took one of the coordinates, right?
Yes, sir.
But I can recover the other coordinate in terms of this. I'm using only one slot to describe this. To put a coordinate system, I used only some of the slots, only one slot. But the point can be recovered from it.
Yes, sir.
Right.
Yes, sir.
So you see, as a dictionary, I do not have to carry around those two. So if I want to describe this point, I do not have to carry around those two coordinates. I can simply carry around one coordinate and I keep the dictionary in hand.
Okay, and in our general setting, this is what F is. F is the dictionary.
Yeah, that is one way. But you see now, there are other ways of thinking of this. You see what, and this is a more interesting way of thinking about it. Let us suppose I have some manifold. Okay, let's just suppose I have some Rn. Okay, now now this is a different thing. Okay, now my manifold itself is R2, so there is no patching or anything required. The whole thing itself is R2. However, now I have a function from R2 to R, which is a different manifold. And the function is x comma y goes to x square plus y square.
Okay. Okay.
Under what condition can I say that level sets of this function are themselves manifolds? And the implicit function theorem is something that is going to tell you that I can identify a level set. I can say that a level set is actually a manifold. Notice that if I take the level set at level -1, it is not a manifold. It is empty. The function is x square plus y square.
Yes, sir.
If I take the level set at level 1, it is a manifold. Because that x, the x, you see the recovering y in terms of x, effectively this is telling me that the set w, I don't have to keep track of that function f at all, because because whatever the remaining part of whatever this level set is can be recovered in terms of x uniquely. So that set w is really identified with, okay, so if we can, so if we go back, let us see. You see the set w is really a proxy for the entire, so the set w, the set of all x in w, which is w, is really proxy for the set x comma f of x.
So I didn't quite follow this.
Yeah, so what I'm saying is, you see the level set is the locally the level set is really the set of all things of the type x comma f of x.
Yes, sir.
Right? So if I want to show that this is a manifold, but
Yes, sir.
but really speaking, this set x comma f of x for all x in w is really the same as w up to identification. It's a bijection, right? It's a bijection both ways. Okay, let's do it like this. Okay, so to give you an example, what is happening is very similar to the following. Let us suppose I have a map. Let's suppose I have a linear map from a 7-dimensional space to a 5-dimensional space, which is surjective.
Yes, sir.
The kernel of this map is 2-dimensional, right?
Yes, sir.
Is it equal to R2? No. It is a thing that has I mean, it is a bunch of vectors, each one of which has 7 coordinates.
Yes, sir. Yeah.
However, I can just say, look, for all practical purposes, it is R2. It is not equal to R2. It is isomorphic to R2. But if I want to do any work with this set, then I just have to keep track of 2 coordinates. No, the remaining 5 coordinates can be obtained in terms of these 5.
Yeah.
Right?
Yeah.
So conceptually, it is just R2.
Yes, sir.
That's exactly what is happening over here. I am saying that this level set locally near the point A comma B, locally it is of the type x comma f of x. But x is varying over all of w. So I can simply use w as a proxy for this local portion of the level set.
Yeah, I see.
So you see, as far as putting coordinates of this are concerned, the f is not, I can recover the f part, ignore it.
Right.
Right? So if I want to think of this geometrically, then it is just like an open set of, so whatever this level set may be complicated, but locally it is just a part of whatever, just w, which is just, so I can think, so you see, I can think of it as a ball. As far as its geometric nature is concerned, it is just a ball, d-dimensional ball.
Okay, and therefore the level set must be a manifold by.
Now if this holds everywhere, and in fact we have sort of almost done it. So if we see, if this surjectivity condition is true if the surjectivity condition is true at every inverse image of A, at every inverse image of C, at every A comma B that gets mapped to C, if this surjectivity condition is true for the derivative map, then what have I said? That around every point, every such point P, I have put an, I have said that locally the solutions look just like an open set of RD. That means I have made this level set into a manifold. It may be a very
Okay.
complicated, see, globally, it may be a very complicated thing. I do not know what it is. But just checking this linear condition, take the Jacobian, see if it is surjective. If I'm able to show this, then I know that locally this looks just like RD. A ball in RD, which is like RD. So I have shown that this is a manifold. You see, to appreciate this, you have to see some examples of manifolds. So you see circle, okay, circle, I can see already, look, I can see the circle everywhere. I can put a little arc. But now imagine, see, a circle is like saying, it's the set of all directions. A circle can be identified with a set of all directions in R2, right?
Yes, sir.
So, so sometimes sets that do not obviously have a geometric structure, I can make them geometric. So the set of all directions in R2 can be thought of as circle, and I can put a geometric structure on that. The set of all directions in R3 is a sphere. Now let's change this slightly, and let us say, let's take the set of all lines in R2. So is it clear that this is a manifold? So set of all lines in, sorry, not all lines to the origin. So the set of all lines in R2 is going to be like this. Is it clear that this set has a geometric structure? Well, I mean, it sort of depends on how I put it. But the point is, I can think of each line as the intersection of each line with this, and every line will now be represented by two diametrically opposite points. So I can think of this geometrically as the circle where the two opposite points are identified. So equivalence classes of these things. Now, is it clear that, okay, so somehow I want to say that this line and this line, they are close to each other, and this line is not as close. So how can I make this a geometric set? And notice that this is really almost like a semicircle, because every line can be identified with the way it intersects this semicircle, and every line will intersect this semicircle exactly once, except this line, right? Except the horizontal diameter.
Yeah.
So as geometrically, what this is that it is the semicircle, any semicircle you can take, but with the endpoints identified. So you see, this is also like a circle.
Oh, yes, sir.
Right.
Yeah.
However, now if I go to 3 dimensions and play the same game, so this is RP2.
Yeah, we have to identify all points on the equator.
Exactly, in R3. So then I get a hemisphere, and now this becomes a completely weird set. So you see, this is a. Now on the equator, I have to identify all diametrically opposite points. So what can I do? On the equator, I can just take half the equator. So you see, it's a weird set. So I can throw away the dotted part. But then these 2 points still need to be identified. So it's kind of weird. These 2 points are close to each other. And that means if I take some points in the upper part of the hemisphere that are close to those respective points, they may look far, but they really are close to each other. So this is a set that cannot be really, I mean, this requires proof, but this is a set. If I give this geometric structure to it, it is not something that can be realized inside R3. But nonetheless, this is a perfectly beautiful manifold. Because see, all points are like all other points. You know, I mean, all directions are the same, no, here. So if I look over here, then I can put a perfectly nice patch around it.
Right.
So this is a manifold. It's a, locally it is like it's a 2-dimensional manifold. This particular way of understanding it somehow makes things near the equator weird, but there is nothing weird about them.
Right. I guess if I zoom in, they still will look like R2. I can still
But you
put my-
see, no, if I choose the point is I'm going to patch it in different ways, you see,
Okay. Okay.
right? So because I can do this for every equator, no, for every great circle, I can do this. So this is like putting different coordinates. So basically what am I doing? For all points that are not on the equator, this looks just like the upper hemisphere. So this is exactly like R2. But I do it around every hemisphere, but I do it around around every, around every equator, or like what I did in the circle case. What can I do here? If I just see the smallest number is, for example, if I do for 4 of them, the upper and the lower semicircle, and then the left and the right semicircle. By the way, I'm now mixing very different things. Okay, so here I was talking about the circle. The real projective space is different, but I can have enough of these hemispheres so that they patch together to give me the entire thing.
Right.
Okay.
Yeah.
So, by the way, so this was a very chaotic discussion, but I hope you got something out of it. One precise thing that I would like to say is that the implicit function theorem will allow us to show that if I have a map from one manifold to another, or let's just say Rm plus n to d plus m to some Rm, such that the surjectivity condition is met at every point of a level set. Okay, so I hope you got that. That is the assumption, right?
Yes,
then the implicit function theorem hands us on a platter that this level set is a manifold.
right. I think I
Because at every point I have gotten this neighborhood W of RD, and I can just use that as my address. I do not have to worry about the f of x. That is just, that is decided by everything. Just like the linear situation that I told you. Remember, if I have a map from R7 to R5 and it is surjective, and if I want to work with the kernel, I can pretend that it is R2.
Yes,
I have to carry only 2 coordinates. The remaining coordinates will be decided in terms of them. That is the linear situation. The thing that is happening over here, which is, transiting from linear algebra to calculus and to geometry more generally, is that in geometry, what I have to do is this is happening locally. So I have to keep track of this as many different points. But locally, what is happening is just linear algebra. That somehow is the essence of these implicit function theorems, inverse function theorem. That is what is the essence. And you should try to formulate this for yourself. Just like there is this thing where I have a local surjection. Locally, at a point the derivative is a surjection. Similarly, there should be some version where locally it is an injection.
Okay.
And the rank theorem tells you that, okay, so if I have a general linear, if I have a general arbitrary linear map, then what does it say? See, for an arbitrary linear map, what can I do with it by changing basis in source as well as target? I can make it as identity of the size as the rank, and all the other entries 0, correct?
Yes, sir.
Right. So that's the linear version. So the rank theorem is going to tell you, so if you look at it in Rudin, then it is going to tell you that for a general, in a general case where the derivative has a certain rank, how can I locally have a certain form for that, for the map so what we are doing is we are trying to say locally, how does a function look based on how its derivative behaves. The simplest thing was that if the derivative is an isomorphism look at a certain point, and therefore locally the derivative is going to be an isomorphism, right? See, this is where the C1 is coming from. If the determinant is non-zero at a certain point, then the determinant will be non-zero in a neighborhood.
Yes, sir. Yeah.
So then it says that, okay, so that means that I can put the function locally itself in a certain form. The function itself is going to be invertible locally, just because the derivative is invertible. That is the simplest form. The
Okay.
implicit function theorem said that if the derivative is surjective, then that means that the function locally itself I can solve for some coordinates in terms of other coordinates. This was exactly like the linear algebra situation. When the map is surjective, I was able to solve for the pivot variables in terms of the free variables.
Okay. Okay.
So the general rank theorem or the other part, which is the local injection, that is also going to have analogous statements. And those statements have some kinds of those statements will have some implication in terms of manifolds when you will define them.
Okay. Okay.
But again, I have to say that this is something that one has to meditate on, right? It's not something that just sort of comes right in.
Okay. Okay. I think this was helpful, sir. I think I'm sort of seeing more of the bigger picture now. Thank you very much, sir. I think that was quite helpful.
Okay, so I think, yeah, we went for quite a while today. So let's stop. We will have the quiz on Sunday, and then Monday's class we will definitely have. But the rest of the week, it's up to you. So, all right, bye everyone.
Thank you very much.